We are not going for a nap. We are going to listen to our next speaker. And the next person being here on stage speaking is a person who has studied chemistry at the University of Duisburg-Essen, and she received her Ph.D. with honors in 2022. And Anna, she will let us know about a very brilliant new idea she came up with. And I just give you a hint, you might not need to wait so long for your cold brew anymore. So,
good to hear. Everyone, please a warm welcome for Rosa Ziefuß. Hey.
Wow, okay. Thank you very much for this nice introduction, and I hope you are all awake and no one is sleeping now. This would be very great. So I will talk today about the ultra-fast cold brewing of coffee by picosecond-pulsed laser extraction. So I'm very at the end of the process chain, right? So we are talking about the brewing method. And you see here already two different pictures, which I just took from journal articles that are describing our research. You see they are looking different, and maybe the one on the right-hand side remembered more on a cold Coke in a disco maybe. But I think it gives you a good impression on what we are currently doing. And I also think the pictures are fun, right? So, but today, and this is my goal for today, I will show you that the research behind this is also fun. But before I do so, let me just shortly introduce a little bit on my background. So you have heard already, I'm a chemist, and my background on coffee is... So I just started with this topic, and this is the first publication on this. Here you see our group structures. So I'm in the laser synthesis and processing of colloids group, where we mainly use the laser to produce nanoparticles. And then we bring the nanoparticles in different applications, like you can see, the biomedicine, the catalysis. We also try to automate the process. And you see my research topic, which is more or less on the surface chemistry, during the process, after the process, and there the coffee totally fits in, right? This was at least my idea. So everything was inspired by Professor Bartschikowski, who is the head of the group, and he tells us still we should broaden our mind and just try to find other applications for our research, and this is exactly what I did. But so the next plan for the next minute is to show you a video where you can get an impression on what is cold brewing. I'm not sure if every one of you is aware of the variant cold brew coffee, and also how is the laser process looking like, right? And now you see the laser process. Okay, so maybe for those who are sitting in the back side and cannot read what there was written, so I was thinking about, okay, cold brewing is nice, we saw this, right? We saw all the nice pictures, but it takes 12 hours. Who wants to wait 12 hours? Me at least not. And more often I just forget that I started to brew the coffee at the next day. So it does not make sense at all. And my idea on this, because my background is lasers, is I will just try to irradiate this with a laser. Maybe also inspired by too much Big Bang Theory. Maybe some of you are knowing this, right? The guys are also irradiating everything with the laser. And the final result was that I can accelerate the brewing time up to 3 minutes. This is at least what I tested. I'm pretty sure there's room for making it even faster. And I'm a chemist. I have no idea about coffee chemistry. I had, at least at this moment. So I wanted to know, okay, what have I produced? Is it still coffee? Did I break down any molecules? Or what do I have there? And to do so, I compared the temperature, the pH value. I also looked at the liquid phase, so the composition of the final product, and the headspace. Don't worry, I will really explain it quite simple. We also published this for those who are maybe interested in this, and I will mainly show results from this publication today. As mentioned, the first parameter is the temperature, right? This is interesting because this is the difference between the hot extraction of coffee and the cold brewed extraction. It's the temperature of the water. And what we find is that the temperature after the laser irradiation stays nearly at room temperature. So at this point, it was already the first hint that we produce a cold brew coffee and not a hot brew coffee. So I will compare everything with both variants. The next thing is we tested the pH value. So we looked, is the coffee acidic? Is it maybe more basic? Which also gives you, I think, already a feeling about the taste profile. And we find, and this is really statistically, and please keep this in mind, that the hot coffee is more acidic than both cold variants. I will come back to this, so this is really a very important point later on. So, and then I looked at the headspace. So just the vapor when I changed the temperature of the coffee, and this is what you typically can smell. And I summarized everything in a table, so you can have later on a look on this. For the moment, you just need to trust me. The only difference that we found between both cold variants and the hot variant is the content of pyridine. So what is pyridine? It's a substance, or what I found in the literature is that it is a strong degradation product of, I don't know how to spell it, trigonolene, so the substance which is written here. It's a bitter alkaloid in coffee, so it makes the coffee more bitter. Okay, so keep this in mind, it's in the headspace. So after evaporating, I find a substance which comes from a bitter alkaloid. This also means that it must be in the liquid phase. So when I now look in the coffee, in the final product, I need to find there the bitter substance. And this was what we did, and yes, we found it. And this really was a big, let's say, problem for me, because the final result is that this means that the cold brew coffee is more bitter than the hot variant. But when you open food blogs, social media, and so on, you will definitely find the difference. So the taste profile, and this is what the peoples are feeling, is that the cold brew variant is less bitter. And I had no idea, and it needed me, I would say, half a year to understand this. It's not necessarily this way. So you can have a product which has more bitter substances, but you feel it's less bitter. And this, in our case, depends critically on the pH value. So hot coffee is very acidic, I mentioned this, and in the acidic range, the human feels bitter substances are more bitterly precised than in the basic regime. And I think this was like a breakthrough, and I also realized there is nearly no research on cold brew coffee. I don't know why, so we are drinking things which are not well analyzed currently, right? Okay, but beside this, I, of course, as a chemist, I was very interested in what is in the liquid and how can I compare it to the hot or the cold variant? And this I did here. So you see on the left-hand side a graphic with a lot of peaks, right? Every peak corresponds to one substance which is included in the coffee. And finally, I do not find any differences in the quality between hot, cold, and the picosecond, so the laser-brewed coffee variant. They are qualitatively the same. But what I see is differences. I mentioned this for the bitter substance already. There is another bitter substance included in coffee, which is caffeine. So we all know this, and I hope this is what you keeps awake during my talk. And there we see that the cold and the picosecond laser, they have a little bit more caffeine than the hot variant. I mean, for the cold variant, it's clear, right? It stays into contact with the liquid for 24 hours, while the hot variant only has 3 minutes or less. And now, for me, started the fun part, right? Because I couldn't believe this result as it is there. So I did further testings. We can have, so I will not go into detail with this, but we can test, we can extract the caffeine, we can weight it, we can measure the mass, we can measure the optical properties, and so on. And all testings showed the same result, that the laser variant, the caffeine content in the laser is comparable with the hot variant. Okay, now you could ask why in my title was written that I produced a cold brew coffee, right? Because in this time it differs. And what chemists are doing then is, so you should not believe everything which you see directly because there are differences, right? So we need to normalize two things. For example, the powder that we used for extraction, because this differs. When you brew a hot coffee, you use a different amount of powder than when you brew a cold brew coffee. The other thing is the temperature will change. And so I just normalized everything. The first plot on the top, you see that the cold variants are making the race. Here I normalized the amount of caffeine to the initial powder. In the next graph, you see that also both cold variants make the race because here I normalized to the temperature. Of course, they are much colder, right? On the third variant, you see that the hot coffee makes the race because there we normalize to the volume to the time, and the cold variant just takes 24 hours. And so on. So it's very difficult to compare, let's say, the amount. Now, and after we published this, we also did a very fair comparison between cold and picosecond laser variant, where we kept all parameters the same. And even there, so we can find the same substances, but also the quantity is different. So the picosecond variant has more extracted parts. I don't know if we really can say it's the same than the cold variant, right? And you also see that there's definitely more research necessary, which is currently hindered by the cold brew traditionally variant is not well understood. Okay, so now I have talked a lot about the experimental data that I got, right? But I haven't talked about the system that I used. So I use a laser system. And there's a pulse written in front of the laser system. So I need to go into detail with this. And I think the images that you saw at the beginning showing, yes, they are fun, but they are scientifically not correct. So when you just look in the lights that you see here, you have light which has a lot of different wavelengths inside. And we are not using this light, obviously, because you see here a red color and a green color. We just cut special regions. And not the red one. The red one will do nothing, just you need to believe me. But the green one, which is in the visible range, it's quite nice. But here you see also a continuous line, which is a continuous laser. So you could ask, can we also do the experiments with a laser pointer? And the answer is clearly no, because you need the pulses. The pulses will, and I tried to illustrate this by the thickness of the lines that you can see. So the continuous laser, it is much thinner than the pulses that you see for the pulse laser system. What we are doing here is we're making the laser on, off, on, off, on, off. And each time when it's off, we put the energy, or we save the energy for the next pulse. So we can create, in principle, incredible high energies for this system. Especially because we are having not just 5 pulses per second, we have 80,000 pulses per second, which is very fast. And we are talking about a length of picosecond. So the off times of the laser are much higher than the on times, right? I don't know if everyone is familiar with picosecond. I mean, maybe you cannot imagine what it means, right? But in a picosecond, the light is just moving, I would say, like this. And light is really fast, right? This also means our laser is really fast, which supports the title Ultrafast Brewing. Okay, then I will come nearly to the last slide, which is, I can imagine when you don't have any idea about the science, then it's like, okay, what does she want to show now? What you see on the left-hand side is a very nice artwork, which comes from my thesis. Currently, I only showed you, or also in the video, you saw a batch process. So as a technical chemist, I would call it a batch process because I'm doing it in a cup of thing to aim the coffee brewing process. But this is inefficient. I have a laser, this is very small, so it's not like this big, it's very, very, very small. So I also need to create a small liquid, and this is what you see kind of vertically. And in there, we have the coffee powder. Just let's say it's a coffee powder. We have the laser, which is coming horizontally. And from my experience and what we did or do currently in our working group, I expected that I will simply cut down the powder. Then my process would be comparable to a traditional milling, right? And this, of course, is good because I make the particles smaller. When I make things smaller, I will increase the total surface area. And so I have more contact area to the liquid, and I can extract more and even faster. But then we realized, so we used here 100 millijoule per square centimeter. So it's the energy density, so the energy that we apply to one spot. But for the coffee process, and I will go with the leopard later into detail, we use much less energy. So you can see it's 1 millijoule. It's just 100 parts of the energy that we use for the fragmentation. This is what we call. So what happens there? We cannot see any smaller particles. So I know that I do not cut them down. And this is now where it becomes also very interesting for our research group, although we are not so experienced in the coffee brewing part, to look into detail, because we found a new regime where we can deal with the laser, where we can make input, and where we can change things. And the idea, I wrote this here as well, is that so you just imagine you make matter hot. You just make something very hot, it's in water. The water is very cold. Then the energy must go somewhere. So, and the easiest way for the energy to go is from the particle to the liquid. But the energy in the particle is, although the energy is very small, it must be very high. So I'm thinking about 200, 300 Celsius increase of temperature. So we expect that there is a bubble which will be created. And in the bubble, we have supercritical fluid conditions. So we have a vapor, maybe, which is very hot, which has a very high pressure. So I'm not even sure if we are talking about a cold brewing process. Is it really cold? Is it hot? I don't know. Is it somewhere in the middle? This is something that we want to go into detail. And I also think that it's very important to go into detail with this, because this is a question to all of you. So just think about this. Is heating of matter in water efficient, energy efficient process, or even cooling? Is this energy efficient? My answer to this is for sure not, because you are heating the whole liquid volume just to get an impact on the coffee powder. But you also heat those parts which are not in contact with the coffee powder directly, right? So you just give energy in the system and it is doing nothing. And this is different for our process. So what we are doing here is we couple the energy directly in the powder. So I'm pretty sure that this process is much more energy efficient than every extraction process that you consider right now. And with this, I want to say, so of course, this is a teamwork as usual, right? So I have a lot of help from my group. I want to thank these guys. I want to thank you for your attention and Probat for the invitation.